Let me ask you something. When you woke up this morning, you probably glanced at a clock. Maybe it said 7:15 or 6:42, or if it was a really good morning, maybe you didn't look at all and just rolled over. But those digits on the screen, those little glowing shapes, they told you something instantly. You didn't have to think about it. You just knew. 7:15. Time to get up or time to stay in bed a little longer. And that tiny, effortless act, reading a number and understanding it, is one of the most extraordinary things a human being can do. Because here's what's wild about it. For most of human history, nobody could do that. Not because people were less intelligent. They were exactly as smart as you and me. But because the idea of a number, the concept itself, had to be invented, discovered, fought over, honestly. And the story of how that happened, how we went from a world with no numbers at all to a world that runs entirely on them, well, that's what we're going to talk about tonight. So settle in, get comfortable. This is a long, slow, beautiful story, and it starts a very, very long time ago. Let's go back, way back. Before cities, before writing, before farming, before pottery. We're talking maybe 40,000 years ago, maybe longer. Somewhere in what's now Central Africa, or maybe Southern Europe, a person picked up a bone, a wolf bone, as it turns out, and started scratching marks into it. Short little lines, one after another. We know this because that bone survived. Archaeologists found it in the 1930s in a place called Lubombo in the mountains between South Africa and Eswatini, and when they examined it closely, they counted 29 notch marks carved deliberately into the surface. 29. Now, we don't know exactly what this person was counting. Some researchers think it was a lunar calendar. 29 days is almost exactly one cycle of the moon. Others think it might have been something else entirely. But whatever it was, someone was keeping track. Someone looked at the world and felt the need to record quantity. Not with words, not with symbols we'd recognize as numbers, just scratches, tally marks. One scratch for one thing, another scratch for another thing. And that impulse, that urge to record how many, that's where everything begins. Think about what that means for a second. Before you can have mathematics, before you can have science, before you can have engineering or economics or computers or any of it, someone has to look at a collection of objects, a pile of fish, a group of days, a herd of animals, and think, I want to remember how many there are. That's not obvious. That's not inevitable. That's a cognitive leap. There's another famous artifact, even older in some ways, called the Ishango bone. This one was found in 1960 by a Belgian geologist named Jean de Heinzelin near Lake Edward in what's now the Democratic Republic of Congo. It's about 20,000 years old, give or take, and it's covered in grouped notch marks that are genuinely puzzling. The marks are arranged in 3 columns, and the groupings in one column go 3, 6, 4, 8, 10, 5, 5, 7. In another column, you find 11, 13, 17, 19. Now look at that second set. 11, 13, 17, 19. Those are all prime numbers. Every single one. Is that a coincidence? Honestly, nobody knows. Some mathematicians have argued that whoever carved the Ishango bone understood something about primes, or at least about odd numbers and divisibility. Others say we're reading too much into scratches on a bone. But either way, the groupings aren't random. Someone was organizing quantities into patterns. And patterns, as we'll see over and over tonight, are the beating heart of mathematics. But here's the thing about tally marks. They work, but only up to a point. If you've got 5 sheep, 5 scratches on a stick is fine. You can glance at it and know. But what about 50 sheep? What about 500? Try scratching 500 marks onto a bone and then counting them back. You'd go out of your mind. And this is the first great problem in the history of numbers. How do you represent large quantities without losing your mind? How do you compress information? For thousands and thousands of years, people solved this problem in small, practical ways. Shepherds in the ancient Near East used a system that's almost heartbreakingly simple. When the sheep went out to pasture in the morning, the shepherd would drop a small clay token into a pouch for each animal. 1 sheep, 1 token. When the flock came back in the evening, the shepherd would pull tokens out one by one as each sheep passed. If there were tokens left over at the end, sheep were missing. No counting required, really. Just one-to-one correspondence. This thing matches that thing. It's the most basic mathematical operation there is, and you can do it without knowing any numbers at all. And those little clay tokens, they turn out to be incredibly important. We're talking about a region called Mesopotamia now, the land between the Tigris and Euphrates rivers, roughly modern-day Iraq. And starting around 8000 BCE, maybe earlier, people in this region were using small clay objects, cones, spheres, discs, cylinders, to represent different goods. A small cone might mean a measure of grain. A sphere might mean a jar of oil. A disc might mean a sheep or a goat. These weren't numbers in the way we think of them. They were more like physical receipts. You're a farmer. You owe the temple 10 jars of oil. So someone makes 10 little clay spheres and puts them in a container. The container itself was often a hollow clay ball called a bulla. And here's what's clever. Before sealing the bulla, they'd press the tokens into the outside surface of the wet clay, leaving impressions. That way, you could see what was inside without breaking it open. Now think about what just happened there. You've got tokens inside a clay ball, and you've got impressions of those tokens on the outside. At some point, somebody must have realized, why do we need the tokens at all? The impressions on the outside carry the same information. And just like that, almost by accident, you've invented writing, or at least the ancestor of writing. Those impressions in clay evolved, over centuries, into the wedge-shaped marks we call cuneiform, one of the earliest writing systems in the world. And the very first things people wrote down weren't poems or prayers or stories. They were accounting records. How much grain? How many sheep? Who owes what to whom? Numbers came before literature. Think about that for a moment. The entire technology of writing, this thing that would eventually give us Shakespeare and scientific papers and love letters, it started because someone needed to count their stuff. The Sumerians, who built the first great cities in southern Mesopotamia, around 3500 BCE, developed something remarkable. They created one of the first true number systems, and it was weird, really weird, by our standards. It was based on 60, not 10 like we use, 60. This is called a sexagesimal system, and if you're wondering why on earth anyone would count by 60s, you're not alone. Scholars have debated this for over a century. One theory is that 60 is an incredibly convenient number because it has so many divisors. You can divide 60 evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Try that with 10. 10 only divides evenly by 1, 2, 5, and 10. So if you're dividing up grain among workers or splitting time into manageable pieces, 60 gives you enormous flexibility. And here's the kicker. You still use the Sumerian base 60 system every single day. There are 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. That's not a coincidence. That's a direct inheritance from people living in mud brick cities in southern Iraq 5,000 years ago. When you look at a clock and see that it's 45 minutes past the hour, you're thinking in a framework that Sumerian scribes developed while sitting cross-legged on reed mats, pressing a stylus into wet clay tablets. The way they wrote numbers was elegant in its own way. They had two basic symbols: a thin vertical wedge made by pressing the corner of a reed stylus straight down, which represented 1, and a thicker, sideways wedge made by pressing at an angle, which represented 10. So to write 23, you'd make 2 fat sideways wedges and 3 thin vertical wedges. Simple enough. But when you got to 60, you'd go back to the thin vertical wedge, now meaning 60 instead of 1. Context told you which value it had. It's a little like how we use the digit 1 to mean 1 in the number 12, but 10 in the number 10, and 100 in the number 100. Position matters, and the Sumerians were among the first people in history to figure that out, though their system wasn't fully positional the way ours is, and it had some quirks that caused real confusion, which we'll get to. But let's slow down for a second, because I want to make sure something doesn't slip past us. What we're really talking about here is abstraction. And abstraction is the secret engine of everything that follows in this story. See, a tally mark isn't abstract. 1 scratch means 1 sheep. It's concrete, physical, tied to a specific thing. But when a Sumerian scribe writes a symbol that means 7, that 7 isn't 7 sheep or 7 jars of oil or 7 anything in particular. It's just 7. The pure idea of 7-ness, stripped away from any specific object. That is a staggering intellectual achievement. It took thousands of years to get there. And once you have it, once you can think about numbers as things in themselves rather than just descriptions of other things, the entire world opens up. You can start asking questions like, what happens when I combine this 7 with that 3? What's the relationship between these quantities? You can start doing mathematics. And that's exactly what the Sumerians and their successors, the Babylonians, started doing. The Babylonians inherited the Sumerian number system and ran with it. By around 1800 BCE, Babylonian scribes were solving what we'd now call quadratic equations. They could calculate the square root of 2 to remarkable accuracy. Their value, converted to our decimal system, works out to about 1.41421, which is correct to 5 decimal places. They had multiplication tables, tables of reciprocals, tables of squares and cubes. They could handle problems involving compound interest, land surveying, construction planning. All of this on clay tablets, in a number system based on 60, more than 3,500 years ago. There's a particular tablet, known today as YBC 7289. It's in the Yale Babylonian collection, hence the name. And it's just a small clay disc, fits in the palm of your hand. On it, someone drew a square with its 2 diagonals, and along one of the diagonals, they wrote numbers. When scholars decoded those numbers, they found the value of the square root of 2, expressed in base 60. The accuracy is extraordinary. Whoever made this tablet understood the relationship between the side of a square and its diagonal. They knew, in practical terms, what we'd now call the Pythagorean theorem, more than 1,000 years before Pythagoras was born. And this is something that comes up again and again in the history of numbers. Ideas that we associate with one famous person or one particular culture often have much deeper, older roots. The story is never as clean as the textbooks make it sound. It's messier, more distributed, more human. Knowledge doesn't appear in a flash of genius. It accumulates, layer by layer, in dozens of places, carried forward by people whose names we'll never know. Meanwhile, something very different was happening along the Nile. The Egyptians had their own number system, and it worked in a way that would feel more familiar to you because it was based on 10. They had distinct symbols for 1, 10, 100, 1,000, 10,000, 100,000, and 1,000,000. A single stroke for 1, a heel bone shape for 10, a coiled rope for 100, a lotus flower for 1,000, and the symbol for 1,000,000 was a figure of a god with arms raised, as if overwhelmed by the enormity of the number, which is kind of wonderful when you think about it. Their system was additive, meaning you just pile up symbols to make a number. To write 365, you'd draw 3 coiled ropes, 6 heel bones, and 5 strokes. The order didn't technically matter. You could arrange them however you liked, though scribes tended to put the larger values first. It's straightforward, and it worked perfectly well for record-keeping, taxation, and the massive construction projects the Egyptians were famous for. But it had a limitation that would matter more and more as mathematics grew more sophisticated. It wasn't positional. The symbols always meant the same thing, regardless of where you put them. A heel bone was always 10, whether it appeared at the beginning or end of a number. And that meant the system couldn't easily handle the kind of compact, flexible notation that would eventually make advanced calculation possible. But the Egyptians were brilliant practical mathematicians nonetheless. We know this largely because of a single document, one of the most precious mathematical texts in existence. It's called the Rhind Papyrus, named after the Scottish antiquarian Alexander Henry Rhind, who bought it in Luxor in 1858. The papyrus itself was written around 1550 BCE by a scribe named Ahmes, and Ahmes tells us he's copying from an even older document, dating to maybe 1850 BCE. It's essentially a math textbook. 84 problems covering arithmetic, fractions, geometry, and practical applications like calculating the volume of a cylindrical granary, or figuring out how many loaves of bread you can make from a given amount of grain. And the way the Egyptians handled fractions is fascinating because it's completely different from anything you learned in school. They almost exclusively used what we call unit fractions, fractions with 1 in the numerator. So instead of writing 2/5, they'd express it as 1/3 plus 1/15. Every fraction got broken down into a sum of distinct unit fractions. They had extensive tables for these decompositions. It seems cumbersome to us, but it worked, and it persisted for thousands of years. There's a kind of stubborn elegance to it, a commitment to a particular way of seeing the world that shaped everything they built. And what they built, of course, was extraordinary. The Great Pyramid of Giza, constructed around 2560 BCE, required calculations of volume, slope, alignment, and labor management on a scale that boggles the mind. The base is level to within just a couple of centimeters across more than 230 meters. The sides are aligned to true north with an accuracy of about 1/12 of a degree. You don't achieve that kind of precision without serious mathematical capability. The Egyptians had a concept they called the seked, which was essentially the horizontal distance for every unit of vertical rise, an ancient version of what engineers now call the slope or gradient. For the Great Pyramid, the seked works out to about 5.5 palms per cubit of height, giving that iconic 51-degree angle that makes the whole structure look so perfectly proportioned, so solid and eternal against the desert sky. And here's what's remarkable. That sect system meant that every stone cutter, every work crew hauling blocks up those ramps, could independently verify that their section of the pyramid was maintaining the correct angle. You didn't need a master architect standing over every shoulder. You just needed the number. 5.5 palms per cubit. That's the power of a shared mathematical language. It scales. It lets thousands of people coordinate toward a single geometric vision. But Egypt and Mesopotamia, as extraordinary as they were, weren't the only places where numbers were being shaped into something powerful. And this is where the story opens up. Because if you pull back and look at the ancient world as a whole, you start to see parallel experiments happening. Different civilizations, often with no contact with each other, arriving at their own ways of encoding quantity, their own notations, their own insights. And some of those systems were, honestly, more elegant than anything the Mediterranean world came up with for centuries. Let's talk about China. Because the Chinese numeral system is one of the great underappreciated achievements in the history of mathematics. By the time of the Shang dynasty, around 1200 BCE, the Chinese were using a decimal system, base 10, just like we use today, inscribed on oracle bones. These were pieces of turtle shell or animal bone used for divination, and the numbers carved into them are clear, organized, and unmistakably positional in their thinking. They had distinct symbols for 1 through 9, and then separate symbols for 10, 100, 1,000, 10,000. The way you combined them was essentially multiplicative. You'd write the symbol for 3, followed by the symbol for 100 to mean 300. It's clean, it's intuitive, and it maps remarkably well onto spoken language, which is something not every number system manages. But here's where it gets really interesting. By around the 4th century BCE, Chinese mathematicians were using counting rods, small bamboo or ivory sticks laid out on a flat surface in specific patterns to represent numbers. And the system they developed for these rods was fully positional, meaning the value of a rod pattern depended on which column it sat in. Just like our modern system, where a 3 in the hundreds column means something completely different from a 3 in the tens column. They even alternated between 2 different styles of rod arrangement, vertical rods for odd place columns and horizontal rods for even place columns, specifically to make it easier to read and avoid confusion. Think about that level of design thinking. That's not just math, that's user interface. And the counting rod system wasn't just for recording numbers. It was a computational tool. You could add, subtract, multiply, divide, all by physically manipulating these rods on a board. It was, in a real sense, an ancient calculator. And Chinese mathematicians pushed it far. The 9 chapters on the mathematical art, a text compiled around the 1st century CE, but containing material that's probably centuries older, covers an astonishing range. Areas and volumes, proportions, taxation calculations, systems of simultaneous linear equations solved by a method that's essentially Gaussian elimination, about 1700 years before Gauss. They were working with negative numbers too, using red rods for positive quantities and black rods for negative ones. Red and black, positive and negative. A physical, tangible representation of a concept that European mathematicians would struggle with and resist well into the Renaissance. Now, here's a thread worth following: negative numbers. Because the story of how different cultures handled the idea of less than nothing tells you so much about how mathematical thinking evolves. The Chinese accepted negative numbers almost matter-of-factly. They were a practical tool for balancing accounts, for solving equations where quantities sometimes went below 0. It just made sense. If you owe someone 3 bushels of grain, that's -3. The rods on the counting board made it concrete. You could see it, touch it, move it around. Indian mathematicians, too, embraced negative numbers relatively early. Brahmagupta, writing in the 7th century CE, laid out rules for arithmetic with negative numbers. What happens when you multiply a negative by a positive by a negative? He called positive numbers fortunes and negative numbers debts, which is wonderfully practical. And he got the rules right. A debt subtracted from zero is a fortune. A debt multiplied by a debt is a fortune. These are the sign rules you learned in middle school, and Brahmagupta had them nailed down around 628 CE. But let's not jump too far ahead. Let's stay with India for a moment, because the Indian contribution to the history of numbers is, and I don't think this is an exaggeration, the single most important one. And it comes down to something so fundamental, so woven into the fabric of modern life, that you probably never think about it at all. Zero. Now, the idea of zero has layers to it, and they're worth teasing apart. There's zero as a placeholder, a way of indicating an empty position in a number. The Babylonians eventually developed a placeholder symbol, a pair of small wedges, to distinguish between, say, what we'd write as 205 and 25. Without that placeholder, their positional system could be genuinely ambiguous. But the Babylonian placeholder wasn't really a number. It was a punctuation mark, a way of saying, nothing goes here. It didn't participate in calculations. You couldn't add it to something or multiply by it. It was a gap marker. The Maya, independently, also developed a zero, a shell-shaped glyph used in their vigesimal, or base 20 system, and theirs appeared possibly as early as the 4th century CE, maybe earlier. It functioned as a placeholder in their long count calendar, that extraordinary system for tracking vast stretches of time. The Maya zero is a genuine intellectual achievement, arrived at completely independently from anything happening in the Eastern Hemisphere. But like the Babylonian version, it remained primarily a positional tool within a specific notational context. What happened in India was different. What happened in India was that zero became a number, a full citizen of the number line, with its own properties, its own rules, its own behavior in arithmetic. And that transformation, from placeholder to number, is one of the great conceptual leaps in all of human thought. The history is a bit murky, and scholars still debate the exact timeline, but here's the rough shape. By the 5th century CE, Indian mathematicians were using a fully place-value decimal system, the direct ancestor of the numerals you use every day. The earliest clear evidence we have of the modern decimal place-value system, including a symbol for zero, comes from Indian sources. There's a famous inscription at a temple in Gwalior, dating to 876 CE, that contains the number 270 written in a form that's unmistakably the system we use now. But the mathematical tradition behind it is older. Aryabhata, writing around 499 CE, used a place value system in his calculations, though his notation for zero is debated. Brahmagupta, that same mathematician who sorted out negative numbers, explicitly defined zero and laid out rules for computing with it. Zero plus a number is that number. Zero times a number is zero. And then he ventured into trickier territory. What about zero divided by a number? That's zero, he said. Fine. But what about a number divided by zero? Here, Brahmagupta stumbled a bit, suggesting the result was a fraction with zero in the denominator, which doesn't quite work. It would take later mathematicians to fully grapple with why division by zero is so problematic, why it doesn't just give you infinity, but rather breaks the logical structure of arithmetic itself. But the point is, by the 7th century, Indian mathematicians had assembled all the pieces of what we now call the Hindu-Arabic numeral system, 10 digits including zero, a fully positional decimal notation, and a set of arithmetic rules that worked seamlessly across addition, subtraction, multiplication, and division. This is the system. This is what's on your phone screen right now, what's printed on every price tag, what runs through every computer on Earth. and it came together in India through the accumulated work of generations of mathematicians whose names, Aryabhata, Brahmagupta, later Mahavira, Bhaskara, deserve to be as famous as any in the history of science. Now, having a brilliant system is one thing. Getting the rest of the world to adopt it is another story entirely. And the way Indian numerals traveled westward is a tale that runs through one of the great intellectual crossroads of the medieval world, Baghdad. In the early 9th century, the Abbasid Caliphate was at its height, and Baghdad was arguably the most intellectually vibrant city on earth. The Caliph al-Mamun established the House of Wisdom, or Bait al-Hikmah, a scholarly institution dedicated to translating and building upon the knowledge of every civilization the Caliphate had contact with: Greek, Persian, Indian, Chinese. It was a place where scholars of different backgrounds and traditions came together, and the cross-pollination was extraordinary. And one of those scholars was a man named Muhammad ibn Musa al-Khwarizmi. If that name sounds faintly familiar, it should, because the word algorithm comes from the Latinized version of his name, algorithmi, and the word algebra comes from the title of his most famous book, Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, which you can roughly translate as the compendious book on calculation by completion and balancing. Al-Khwarizmi, working around 820 CE, wrote a treatise on the Indian numeral system that would become the primary vehicle through which these numerals reached the Islamic world and, eventually, Europe. He didn't invent the system. He was clear about its Indian origins, but he explained it, demonstrated its power, and made it accessible. And Al-Khwarizmi's algebra book did something else that was profound. It treated equation solving as a systematic discipline, not just a collection of tricks for specific problems, but a general method. He classified equations into types, showed standard procedures for solving each type, and demonstrated the methods with worked examples. It was practical. Many of the problems involved inheritance law, land measurement, trade calculations. But the underlying approach was abstract and generalizable. You could take his methods and apply them to problems he'd never imagined. Now, here's the thing about the transmission of knowledge. It's never smooth, and it's never fast. The Indian numeral system, championed by Al-Khwarizmi and other Islamic scholars, didn't just waltz into Europe and get adopted overnight. The story of how it finally took hold involves a young Italian merchant's son who traveled to North Africa, learned a different way of doing arithmetic, and came home to write a book that would slowly, grudgingly, over the course of centuries, change everything. His name was Leonardo of Pisa, though you probably know him by a nickname that wasn't even used during his lifetime: Fibonacci. And his story begins in the port city of Bugia, on the coast of what is now Algeria, where his father worked as a customs official, and where the young Leonardo first encountered a system of numerals that made everything he'd learned back home feel clunky and slow. Imagine being maybe 14, 15 years old, and you've grown up doing arithmetic the way everyone in medieval Europe did, with Roman numerals on counting boards, moving little tokens around. You've watched merchants in Pisa laboriously work out their sums, and it functions, it gets the job done. But it's like watching someone try to build a house with their bare hands when there's a perfectly good set of tools sitting right there. And then you arrive in Bugia, this bustling Mediterranean port where traders from across the Islamic world are doing business. And you see how they calculate. You see these 10 simple symbols, including 0, arranged in columns where position determines value. And you watch a merchant multiply 2 large numbers together on a scrap of paper in seconds, and something clicks. Leonardo was transfixed. His father had brought him to Bugia precisely so he could learn the mercantile arts, the practical mathematics of trade. And Leonardo did learn, but he went far beyond what his father probably intended. He didn't just pick up enough arithmetic to manage customs duties. He sought out teachers. He traveled around the Mediterranean, Egypt, Syria, Greece, Sicily, studying with mathematicians wherever he could find them, absorbing everything the Islamic scholarly tradition had developed from those Indian foundations. And then, around 1202, he came home to Italy and published a book called Liber Abaci, the Book of Calculation. Now the title is a little misleading. You might think abaci refers to the abacus, and in a way it does, but not in the way you'd expect. Leonardo wasn't writing a book about how to use an abacus. He was writing a book about how to do calculation with these new numerals, Hindu-Arabic numerals, which would eventually make the abacus unnecessary. The book was massive, over 600 pages in modern editions, and it was essentially a complete course in practical mathematics using the decimal place value system. He started with the basics. Here are the 9 digits, and this special symbol 0. Here's how you write numbers. Here's how you add, subtract, multiply, divide. And then he built up to increasingly sophisticated commercial problems: currency exchange, profit calculations, alloys, all the mathematics a merchant would need. But woven through all of this practical material were problems of real mathematical depth. And yes, this is the book that contains the famous rabbit problem, the one that generates the Fibonacci sequence: 1, 1, 2, 3, 5, 8, 13, and so on, where each number is the sum of the 2 before it. But here's the thing. That problem was a tiny aside in a huge book. Leonardo himself probably didn't think of it as particularly important. The real revolution was the numeral system itself. And Europe resisted. Oh, how Europe resisted. Think about what Leonardo was asking people to do. He was asking an entire civilization to abandon a number system, Roman numerals, that had been in use for over 1,000 years. A system that was literally carved into buildings, stamped on coins, woven into the fabric of legal and commercial practice. And he was asking them to replace it with symbols that came from the Islamic world, which for many Europeans in the 13th century was the domain of the enemy. The Crusades were ongoing. There was deep suspicion of anything associated with Arab culture, even when, as in this case, the thing in question was originally Indian and had been transmitted through Arabic scholarship. Some cities actually banned the new numerals. Florence, in 1299, passed a statute forbidding bankers from using Hindu-Arabic numerals in their books. The stated reason was that the new symbols were too easy to falsify. You could turn a 0 into a 6 or a 1 into a 7 with a quick stroke of the pen. Roman numerals, being more elaborate, were harder to forge, and there was some truth to that concern. But underneath it was something deeper, a conservatism, a distrust of the unfamiliar, a reluctance to abandon the known for the unknown, even when the unknown was demonstrably better. So for a long time, Europe ran 2 parallel systems. Official records, legal documents, and formal accounting often stuck with Roman numerals. But merchants, the people who actually had to do arithmetic quickly and accurately, the people whose livelihoods depended on getting calculations right, they increasingly adopted the new system. They used it in their private books, their personal calculations, their back-of-the-envelope figuring. And slowly, over the course of the 13th, 14th, and 15th centuries, the Hindu-Arabic numerals won. Not because anyone decreed it, not because of some top-down mandate, but because they were simply, undeniably, vastly more practical. Try dividing 1,448 by 37 using Roman numerals alone, without converting to some other system, and you'll understand why. The place value system isn't just a different way of writing numbers. It's a different way of thinking about numbers, one that makes computation almost effortless by comparison. And this is worth pausing on for a moment, because it illustrates something profound about the relationship between notation and thought. The numbers themselves, the abstract quantities, don't change depending on how you write them. 12 is 12, whether you write it as 12 or represent it with 12 pebbles on a counting board. But the ease with which you can manipulate those quantities, the complexity of the problems you can tackle, the speed at which you can work, all of that depends enormously on your notation. A good notation system doesn't just record your thinking, it shapes your thinking. It makes certain operations natural, intuitive, almost automatic, while a poor notation makes those same operations laborious and error-prone. The Hindu-Arabic system, with its place value and its zero, was a cognitive technology as much as a mathematical one. It extended what the human mind could do, with numbers the same way a lever extends what the human body can do with force. By the 15th and 16th centuries, the new numerals had essentially conquered Europe, and this happened to coincide with, and this isn't a coincidence at all, an explosion of mathematical and scientific progress. Once you have a numeral system that makes arithmetic easy, you can start building more sophisticated mathematical structures on top of it. You can develop algebra further. You can create tables of values. You can start doing the kind of systematic calculation that science requires. And speaking of algebra, let's come back to that thread for a moment, because the story of algebra in Europe is fascinating in its own right. Al-Khwarizmi had laid the foundations, and his work had been translated into Latin by scholars like Robert of Chester around 1145. But algebra in the Islamic world and in medieval Europe was still what we'd call rhetorical. Everything was written out in words. An equation wasn't something you could see at a glance, the way you can today. It was a paragraph. The thing plus 3 of its roots equals 40. That's how you'd write what we'd now express as x squared plus 3x equals 40. Every problem was a little essay. The development of symbolic algebra, the use of letters and symbols to represent unknowns and operations, was a slow, halting process that played out over several centuries. And it matters enormously, for exactly the same reason that the shift from Roman to Hindu-Arabic numerals mattered. Notation shapes thought. When you can write an equation as a compact string of symbols, you can see its structure. You can manipulate it. You can spot patterns that would be invisible in a wall of text. One of the key figures in this transition was a 16th century French lawyer named François Viète. Now, Viète is one of those characters who makes you realize that the history of mathematics is stranger than you'd think. He wasn't a professional mathematician. He was a lawyer and cryptanalyst who worked for the French crown, and he was apparently brilliant at breaking coded messages, so good that the Spanish court accused the French of using sorcery to read their dispatches. But in his spare time, Viète worked on mathematics, and around 1591, he published a book called In Artem Analyticum Isagoge, Introduction to the Analytical Art, in which he made a crucial innovation. He used letters to represent not just unknowns, which others had done in various ways, but also known quantities, the coefficients, the given values in a problem, vowels for unknowns, consonants for knowns. This seems like a small thing, but it was transformative. It meant you could write a general equation, not just this specific problem about this specific number of coins, but a template that described an entire class of problems at once. You could reason about equations in the abstract. You could develop general methods and prove they worked for all cases, not just demonstrate them with examples. And this connects to something deeper about what numbers were becoming during this period. For most of human history, numbers were quantities. They counted things. They measured things. 3 sheep, 7 cubits, 12 bushels of grain. But gradually, numbers were becoming more abstract, more detached from the physical objects they originally counted. Negative numbers are a perfect example. We talked about how the Chinese used red and black counting rods to represent positive and negative values, and how Brahmagupta formalized the arithmetic of negative numbers in the 7th century. But in Europe, negative numbers were viewed with deep suspicion well into the 16th and 17th centuries. Mathematicians would encounter them as solutions to equations and call them absurd or fictitious. The great Italian algebraists of the 16th century, Cardano, Tartaglia, Ferrari, names we'll come back to, could solve cubic and quartic equations, which was a stunning achievement. But they'd sometimes reject perfectly valid negative solutions because a number less than nothing simply didn't make sense to them. And if negative numbers were suspicious, imagine how people felt about imaginary numbers. Here's where the story gets genuinely wild, and it starts with one of the great mathematical dramas of the Renaissance, a rivalry so bitter, so personal, and so consequential that it reshaped the landscape of algebra forever. It begins in early 16th century Italy with a professor of mathematics in Bologna named Scipione del Ferro, who around 1515 discovered something that mathematicians had been chasing for centuries: a general method for solving cubic equations, equations involving x cubed. Del Ferro kept his solution secret, which might seem strange to us today, but in Renaissance Italy, mathematical knowledge was a competitive advantage. University positions weren't secure. You held your chair by winning public mathematical duels, literal contests where 2 mathematicians would pose problems to each other, and the one who solved more won. Having a secret method for solving cubics was like having a weapon nobody else possessed. Del Ferro shared his secret with only one person, a student named Antonio Fior. And when Del Ferro died in 1526, Fior decided to use this inherited weapon to make his reputation. He challenged one of the most talented mathematicians in Italy, a self-taught genius from Brescia named Niccolò Fontana, known as Tartaglia, the Stammerer, a nickname he'd carried since a French soldier's saber had slashed his jaw and palate when he was a boy during the sack of Brescia in 1512. Tartaglia had survived that wound, taught himself mathematics from borrowed books, and become one of the sharpest minds in Italy. And when Fior challenged him to a public contest, posing 30 cubic equations, Tartaglia didn't have Del Ferro's method. He had to figure it out himself. And on the night of February 12th, 1535, working frantically as the deadline approached, he did. He cracked it, all 30 of them, in a single night. Fior, meanwhile, couldn't solve the problems Tartaglia had posed in return. The contest was a rout. Tartaglia had independently rediscovered, and possibly extended, Del Ferro's secret method for solving cubic equations, and he'd done it under pressure, against a ticking clock, fueled by nothing but raw brilliance and the terror of public humiliation. Now, you'd think that would be the end of the story. Tartaglia wins. Fior fades into obscurity, and mathematics moves on. But this is where it gets complicated, because there was another mathematician watching all of this very closely, a man named Girolamo Cardano. And Cardano is one of those figures in history who's almost impossible to pin down. He was a physician, a gambler, an astrologer, a philosopher, a mathematician, and by most accounts, one of the most brilliant and difficult people in 16th century Europe. He was born in Pavia in 1501, the illegitimate son of a lawyer who happened to be a friend of Leonardo da Vinci. His life was a cascade of drama. He struggled to get his medical degree because of his illegitimacy. His son was later executed for poisoning his own wife, and Cardano himself was eventually arrested by the Inquisition for casting the horoscope of Jesus Christ. I mean, this is not a boring person. But Cardano was also a genuinely gifted mathematician, and when he heard about Tartaglia's triumph over Fior, he became obsessed with learning the method for solving cubics. He approached Tartaglia repeatedly, flattering him, pleading with him, and eventually, in 1539, Cardano convinced Tartaglia to reveal the secret, but only under a solemn oath. Tartaglia made Cardano swear that he would never publish the method, and Cardano agreed. Here's the thing, though. Once Cardano had the method and started working with it, along with his brilliant young student Lodovico Ferrari, he realized something. First, he and Ferrari extended the work dramatically. Ferrari figured out how to solve Quartich equations, the next step up, equations with x to the fourth power, by cleverly reducing them back to cubics. That alone was a monumental achievement. But then Cardano discovered something else. He found evidence that Scipione del Ferro had actually solved cubics before Tartaglia. He tracked down del Ferro's original notes, held by del Ferro's son-in-law in Bologna. And this gave Cardano what he felt was a moral loophole. He'd sworn not to publish Tartaglia's method. But del Ferro's method? He'd made no such promise about that. So in 1545, Cardano published his masterwork, the Ars Magna, the Great Art, and in it, he laid out the complete solution to cubic and quartic equations, crediting del Ferro with priority and Tartaglia with independent rediscovery. It was, by any measure, one of the most important mathematics books ever written. And Tartaglia was absolutely furious. He felt betrayed, and honestly, it's hard to blame him entirely. The oath had been clear. The two men exchanged bitter public letters, and Ferrari, loyal to his teacher Cardano, challenged Tartaglia to a public debate in Milan in 1548. Tartaglia reluctantly accepted, and by most accounts, Ferrari won. Tartaglia's reputation suffered, and he spent the rest of his life nursing the grievance. Now, you might be thinking, okay, this is great drama, but what does solving a cubic equation actually have to do with the history of numbers? And the answer is everything. Because when Cardano and his contemporaries worked through the formula for solving cubics, what we now call Cardano's formula, even though the credit is tangled, they ran headlong into something deeply unsettling. The formula worked. It gave correct answers. But in certain cases, right in the middle of the calculation, it required you to take the square root of a negative number. Think about what that means. We talked earlier about how people were already uncomfortable with negative numbers, how even sophisticated mathematicians resisted the idea that you could have less than nothing. Now imagine being told that to solve a perfectly reasonable equation, one with a perfectly real, positive answer that you could verify, you had to pass through a step that involved the square root of -1. A number that by every intuition you possess cannot exist. You can't square any real number, positive or negative, and get a negative result. 2 times 2 is 4. -2 times -2 is also 4. There is no number on the number line whose square is -1. And yet, the formula demanded it. And if you just held your nose, treated these impossible square roots as if they were legitimate numbers, manipulated them according to the usual rules of algebra. They would cancel out at the end, and you'd be left with the correct real answer. It was like walking through a wall to get to the room on the other side. The wall shouldn't be passable, but somehow, if you just kept walking, you ended up exactly where you needed to be. This was genuinely disturbing to 16th century mathematicians. Raffaele Bombelli, an Italian engineer and mathematician working in the 1570s, was one of the first to take these strange quantities seriously. He didn't call them imaginary numbers. That dismissive label came later, from Descartes in the 1600s, and it stuck, which is a shame, because it makes them sound fake when they're anything but. Bombelli simply worked out consistent rules for how to manipulate them. He said, look, I don't know what the square root of -1 is, but if I define it as a thing and work out how it behaves, when you add it, multiply it, raise it to powers, then everything comes out consistent. He called these quantities plus of minus and minus of minus, and he showed that you could use them to extract real solutions from Cardano's formula in exactly those troublesome cases. And here's what's really beautiful about this. Bombelli didn't have a philosophical justification for why these numbers should exist. He had a practical one. They worked. The formula demanded them, and when you trusted the algebra, you got correct answers. This is one of those moments in the history of numbers where utility runs ahead of understanding. The numbers showed up uninvited, proved they were useful, and then humanity spent the next few centuries figuring out what they actually were. It took until the 19th century for mathematicians to fully make peace with complex numbers. Numbers that combine a real part and an imaginary part. And the key insight came from a beautifully simple geometric idea. If real numbers live on a line, a one-dimensional number line stretching from -infinity to +infinity, then complex numbers live on a plane. The real part goes left and right, the imaginary part goes up and down, and every complex number is a point on this two-dimensional surface. Multiplying by the square root of -1, which we now just call I, corresponds to a 90-degree rotation. That's it. That's all it is. Not some mystical impossibility, just a rotation in a plane. Caspar Wessel, a Norwegian-Danish surveyor, published this geometric interpretation in 1799, though hardly anyone noticed at the time. Jean-Robert Argonne, a Swiss bookkeeper, not even a professional mathematician, independently published a similar idea in 1806. And then Gauss, who we'll come back to because Gauss shows up everywhere, used the geometric picture extensively and gave complex numbers full mathematical respectability. And today, complex numbers are everywhere. They're not exotic curiosities. Electrical engineers use them constantly. Alternating current, the stuff that powers your home, is naturally described by complex numbers because voltage and current oscillate like waves, and waves involve rotations, and rotations are exactly what complex numbers capture. Quantum mechanics, the physics of atoms and subatomic particles, is built on complex numbers at the most fundamental level. The wave function that describes the state of a quantum system isn't real valued. It's complex valued. Without complex numbers, you literally cannot write down the equations that govern the behavior of matter at the smallest scales. Signal processing, control theory, fluid dynamics, complex numbers are woven into the fabric of modern engineering and science, all because some Renaissance mathematicians had the courage to keep calculating even when the intermediate steps looked impossible. So let's step back for a moment and appreciate what happened between, say, the 12th and 16th centuries. When Fibonacci wrote Liberace in 1202, Europe was still doing arithmetic with Roman numerals and counting boards. By the time Bombelli published his algebra in 1572, European mathematicians had Hindu-Arabic numerals, symbolic algebra, solutions to cubic and quartic equations, and the first serious engagement with complex numbers. That's an extraordinary acceleration. And it happened because of a chain of human connections. Al-Khwarizmi's books traveling to North Africa, a young Fibonacci learning from Arab merchants, Italian mathematicians challenging each other to public duels, a secret passed under oath and then broken, and an engineer named Bombelli, who decided that impossible numbers deserved to be taken seriously. But here's something we haven't talked about yet, and it's one of the most profound shifts in the entire history of numbers. Everything we've discussed so far, integers, fractions, negative numbers, even complex numbers, these are all, in a sense, countable or constructible. You can write them down as ratios or as finite expressions involving square roots and cube roots. But lurking beneath the surface of mathematics, there's a vastly larger world of numbers that can't be captured that way. Numbers that go on forever without repeating. Numbers that can't be expressed as any fraction. Numbers that slip through every algebraic net you try to cast. And the story of how humanity discovered these numbers, and how deeply unsettling that discovery was, begins, of all places, in ancient Greece, with a cult of philosopher-mathematicians who believed that the universe was built entirely out of whole numbers and their ratios, the Pythagoreans. And what they found shook them to their core. The Pythagoreans weren't just mathematicians. They were something closer to a religious brotherhood, a secretive community founded in the 6th century BC in Croton, a Greek colony in what's now southern Italy. Pythagoras himself, and honestly, separating the real Pythagoras from the legend is almost impossible at this point. He was born on the island of Samos around 570 BC, traveled widely, possibly to Egypt, possibly to Babylon, and eventually settled in Croton, where he gathered a devoted following. These followers lived by strict rules. Some accounts say they wouldn't eat beans. They believed in the transmigration of souls, and at the center of their worldview was a single beautiful conviction. That number is the essence of all things, not just a tool for counting or measuring, but the fundamental substance of reality itself. And when they said number, they meant whole numbers and ratios of whole numbers, what we'd call rational numbers. To the Pythagoreans, every relationship in the cosmos could be expressed as a ratio, and they had good reason to believe this, because they'd discovered something genuinely profound about music. If you take a vibrating string and pluck it, you get a note. Now divide that string exactly in half and pluck it again. You get a note 1 octave higher. The ratio is 2 to 1. Divide it so 2/3 of the string vibrates and you get a perfect fifth, 3 to 2. 3/4 gives you a perfect fourth, 4 to 3. The most beautiful harmonies in music corresponded to the simplest ratios of whole numbers. Think about how magical that must have felt. The experience of beauty, actual aesthetic pleasure, the thing that makes a chord sound consonant rather than dissonant, was governed by precise numerical relationships. If music was ratio, then maybe everything was ratio. Maybe the planets moved in ratios. Maybe the soul itself was a kind of harmony, the whole universe singing in fractions. It's a gorgeous idea. And it's wrong, or rather, it's incomplete in a way that turned out to be devastating. Here's what happened. Someone in the Pythagorean community, tradition often credits a man named Hippasus of Metapontum, though the details are murky and debated, discovered that certain quantities simply cannot be expressed as a ratio of 2 whole numbers. The classic example and almost certainly the original one, involves the simplest geometric construction imaginable: a square with sides of length 1. Picture a square. Each side is exactly 1 unit long. Now draw a diagonal from one corner to the opposite corner. How long is that diagonal? Well, by the Pythagorean theorem, their own theorem, the diagonal squared equals 1 squared plus 1 squared, so the diagonal squared equals 2. The diagonal is the square root of 2. And here's the crisis. The square root of 2 is not a ratio of any two whole numbers. It can't be written as a fraction. Not a complicated fraction, not an enormous fraction, no fraction at all, ever. It's irrational. And the proof of this is one of the most elegant arguments in all of mathematics. It's a proof by contradiction, and it goes something like this. Suppose, just for the sake of argument, that the square root of 2 actually is a fraction. Say it equals some whole number p divided by some whole number q. And let's say you've reduced this fraction to its simplest form. P and q share no common factors. Now square both sides. 2 equals p squared over q squared. So p squared equals 2 times q squared. That means p squared is even. And if p squared is even, then p itself must be even. Because an odd number times an odd number always gives an odd result. So p is even, which means p equals 2 times some other whole number. Let's call it k. Substitute that back in. 2 times k squared equals 2 times q squared. 4k squared equals 2q squared. Simplify. 2k squared equals q squared. So now q squared is even, which means q is even too. But wait, you said p and q had no common factors. And now you've shown they're both even, meaning they're both divisible by 2. That's a contradiction. The assumption that the square root of 2 is rational leads to logical nonsense. Therefore, it isn't rational. It can't be. That's it. That's the whole proof. It's been around for roughly 2,500 years, and it's still airtight. No one has ever found a flaw in it because there isn't one. Now, try to imagine what this meant to the Pythagoreans. Their entire philosophy, their cosmology, their understanding of beauty and harmony, and the structure of reality, all of it rested on the belief that everything is ratio. And here was a proof, derived from their own theorem about their own beloved right triangles, that some quantities exist beyond the reach of ratios entirely. The diagonal of a simple unit square, the most basic geometric object you can draw, has a length that escapes the world of fractions. It's not that we haven't found the right fraction yet. It's that no such fraction exists or can exist. The legend says that Hippasus revealed this discovery and was drowned at sea for his blasphemy, thrown overboard by fellow Pythagoreans, or perhaps punished by the gods for exposing a truth the universe wanted kept hidden. That's almost certainly mythological embellishment. But the fact that such a dramatic story attached itself to this discovery tells you something about how deeply disturbing it was. This wasn't just a mathematical curiosity. It was an existential threat to a way of understanding the world, and the Greeks, to their enormous credit, didn't look away. They didn't pretend the problem didn't exist. Instead, they adapted. But here's what's fascinating about how they adapted. They essentially separated geometry from arithmetic. Since numbers, meaning ratios, couldn't capture every geometric magnitude, Greek mathematicians after the Pythagorean crisis became deeply suspicious of treating lengths as numbers at all. Euclid's Elements, written around 300 BC, handles proportions and magnitudes with extraordinary care, using a theory developed by Eudoxus of Cnidus, that essentially works with geometric quantities directly, comparing them through ratios without ever claiming that every length corresponds to a number. It's a brilliant workaround, and it's also, in a way, a retreat. The Greeks had discovered irrational magnitudes, but they didn't develop a number system that could comfortably contain them. That would take a very long time. Let's sit with that for a moment. Think about what the number line looks like. You've got your whole numbers, 1, 2, 3, sitting at regular intervals like fence posts. Between any two of them, you've got fractions. Between 0 and 1 alone, you've got 1/2, 1/3, 2/3, 1/4, 3/4, and on and on. In fact, between any two fractions, no matter how close together, there's always another fraction. The rationals are what mathematicians call dense. They're everywhere. You might think they fill up the number line completely, that there's no room left for anything else. But they don't. They don't even come close. The irrational numbers, the square root of 2, the square root of 3, the square root of 5, and infinitely many others, they fill in the gaps. And here's the truly mind-bending part. There are, in a precise mathematical sense, vastly more irrational numbers than rational ones. The rationals, despite being dense, are countable. You can list them one by one in a systematic way, and eventually you'll reach any particular fraction you name. The irrationals are uncountable. They form a kind of continuous fog that permeates the number line, filling in every microscopic gap between the fractions. But we're getting ahead of ourselves. That particular revelation, the uncountability of the reals, belongs to the 19th century and a man named Georg Cantor, and we'll get there. For now, let's stay with what the discovery of irrationality meant in practice. For centuries after the Greek crisis, mathematicians in various traditions worked with irrational quantities without necessarily worrying too much about their philosophical status. Indian mathematicians computed with square roots freely. Islamic mathematicians handled them with sophistication. When al-Khwarizmi solved quadratic equations, square roots appeared naturally in the solutions, and he simply worked with them. The practical attitude was, these numbers exist. We can approximate them. We can manipulate them algebraically. So let's use them. And that pragmatic approach was enormously productive. But lurking behind the pragmatism was a deeper question that wouldn't fully be resolved until the 19th century. What actually is a real number? What does it mean for a number to have an infinite, non-repeating decimal expansion? How do you rigorously define the continuum, the unbroken line of all numbers, rational and irrational together? Before we get to that reckoning, though, there's another category of number that emerged from the irrational world, and it's even stranger. Among the irrationals, some numbers are at least algebraic. They're solutions to polynomial equations with rational coefficients. The square root of 2 is irrational, yes, but it's the solution to x squared minus 2 equals 0. That's a perfectly ordinary polynomial equation. The cube root of 7, the golden ratio, even complex numbers like I, these are all algebraic. They might not be ratios, but they're still the answers to finite algebraic questions. But in 1844, a French mathematician named Joseph Liouville proved that there exist numbers which are not just irrational, but transcendental, numbers that are not the solution to any polynomial equation with rational coefficients, no matter how high the degree. They transcend algebra entirely. And the two most famous transcendental numbers are ones you already know, The first is e, the base of the natural logarithm, approximately 2.71828, which shows up everywhere in calculus, compound interest, probability, radioactive decay. It's the number that describes continuous growth. Charles Hermite proved it was transcendental in 1873. The second is pi, the ratio of a circle's circumference to its diameter, approximately 3.14159, and Ferdinand von Lindemann proved pi was transcendental in 1882. And Lindemann's proof of pi's transcendence settled one of the oldest open problems in mathematics. For over 2,000 years, geometers had tried to square the circle, to construct, using only a compass and straight edge, a square with exactly the same area as a given circle. It was one of the three great construction problems of antiquity, and Lindemann showed it was impossible, not just really hard. Impossible, because compass and straight edge constructions can only produce algebraic numbers, and pi isn't algebraic. It's transcendental. The tools of classical geometry literally cannot reach it. 2 millennia of effort, and the answer was, it can't be done. There's something almost poignant about that. So by the late 19th century, mathematicians were grappling with a number line that was far richer and stranger than anyone had imagined. You had your natural numbers, your integers, your rationals, your algebraic irrationals, your transcendentals, layers upon layers, each one revealing that the world of numbers was bigger than the previous generation had thought. And it was precisely at this moment, in the 1870s, that two mathematicians working independently decided it was time to put the entire real number system on a rigorous foundation. To answer, once and for all, the question the Pythagoreans had accidentally raised 23 centuries earlier. What is a number, really? One of them was Richard Dedekind, working in Brunswick, Germany. The other was Georg Cantor in Halle. And what they discovered, especially Cantor, would transform not just mathematics, but our understanding of infinity itself. Because Cantor asked a question that sounds almost childishly simple. Are some infinities bigger than others? And the answer turned out to be yes. And the way Cantor proved it is one of the most beautiful arguments in the entire history of human thought. Let's set the stage. It's the early 1870s. Georg Cantor is a young mathematician, still in his 20s, working at the University of Halle in Germany. He's not famous yet. He's been studying trigonometric series, these infinite sums of sin and cosine functions, and through that work, he's been drawn into questions about the nature of sets of points on the number line. What kinds of sets are there? How big can they be? How do you even compare the sizes of infinite collections? These sound like philosophical questions, the kind of thing you might argue about over coffee and never resolve. But Cantor found a way to make them precise, and the tool he used was deceptively simple. It's called a one-to-one correspondence. Here's the idea. Imagine you walk into a concert hall and you want to know whether there are enough seats for everyone. You don't need to count the people and count the seats separately. You just ask everyone to sit down. If every person gets a seat and every seat has a person, the two collections are the same size. That's a one-to-one correspondence. Every element in one set is paired with exactly one element in the other, and nothing is left over on either side. You don't need to know the actual number. You just need the pairing. Now, this works fine for finite collections. But Cantor realized you could apply the same logic to infinite sets, and when you do, things get strange immediately. Take the natural numbers, 1, 2, 3, 4, and so on forever. Now take the even numbers, 2, 4, 6, 8, and so on. Intuitively, you'd think there are fewer even numbers, right? They're a subset. You've thrown away all the odd ones. But Cantor says, can you pair them up? And you can. Pair 1 with 2, 2 with 4, 3 with 6, 4 with 8. Every natural number gets matched with exactly one even number, and every even number gets matched with exactly one natural number. Nothing left over. So in Cantor's framework, the set of natural numbers and the set of even numbers are the same size. They have the same cardinality, to use his term. This already feels counterintuitive. A part is the same size as the whole? But that's actually a defining feature of infinite sets. It's what makes them infinite. An infinite set is precisely one that can be put into one-to-one correspondence with a proper subset of itself. That's wild if you think about it. It's the mathematical version of the old paradox about Hilbert's hotel. The hotel with infinitely many rooms that's completely full, but can always accommodate one more guest by shifting everyone down one room. Infinity doesn't work like finite quantities. It has its own rules. So Cantor explored which infinite sets could be paired with the natural numbers. The integers? Yes. You can list them as 0, 1, -1, 2, -2, 3, -3, zigzagging back and forth. Every integer gets a position in the list. The rationals, all fractions? This one seems harder. There are fractions everywhere. Between any two fractions, there's another fraction. The rationals are, as mathematicians say, dense in the number line. Surely there are more of them than there are natural numbers. But no, Cantor showed you can list them too. The trick is ingenious. Arrange all positive fractions in a grid, the numerator along one axis, the denominator along the other. So you've got 1 over 1, 1 over 2, 1 over 3 across the top row, 2 over 1, 2 over 2, 2 over 3 in the next row, and so on. Every positive fraction appears somewhere in this infinite grid. Now, instead of trying to go row by row, which would never get you past the first row, since each row is infinite, you zigzag diagonally. You go 1 over 1, then 2 over 1, then 1 over 2, then 1 over 3, then 2 over 2, then 3 over 1, and so on, snaking back and forth along the diagonals. Skip any fraction you've already counted in a simpler form, and you get a list. A single, linear list that hits every positive rational number. Pair each one with the natural number marking its position in the list, and you've got your one-to-one correspondence. The rationals are countable, same size as the naturals. At this point, you might start wondering, is every infinite set the same size? Is there just one infinity? And this is where Cantor drops the bombshell. In 1874, he published a paper proving that the real numbers, all the points on the number line, including all those irrational and transcendental numbers we were talking about, cannot be listed. They are uncountable. There is no way to pair them up with the natural numbers. The infinity of the reals is strictly, provably larger than the infinity of the naturals. The proof he's most remembered for came a bit later, in 1891, and it's called the diagonal argument. It's so elegant that it almost feels like a magic trick. Here's how it goes. Suppose someone claims they have a complete list of all real numbers between 0 and 1. Every single one lined up. First real number, second real number, third real number, and so on forever. Cantor says, I can always find a real number that's not on your list. Here's how. Look at the first decimal digit of the first number on your list. Pick a different digit. Say, if it's a 3, write down a 7. If it's a 7, write down a 3. That's the first digit of your new number. Now look at the second decimal digit of the second number. Pick a different digit. That's your second digit. Look at the third digit of the third number. Pick a different one. Keep going forever, down the diagonal of the list. The number you've constructed differs from the first number in its first decimal place, from the second number in its second decimal place, from the third number in its third decimal place, from the nth number in its nth decimal place. So it can't be any number on the list. It's a real number between 0 and 1, but it's not on the supposedly complete list, which means the list wasn't complete after all. And this works no matter what list you start with. There is no possible complete list of the reals. They are uncountable. Think about what that means. The natural numbers are infinite. The rationals are infinite. But the reals are a bigger kind of infinite. There are more points on the number line than there are counting numbers, more real numbers than fractions. Infinity comes in sizes. And Cantor didn't stop there. He showed you could always construct a larger infinity by taking the power set, the set of all subsets of any given set. The power set of the naturals is larger than the naturals. The power set of that is larger still. There's an endless tower of infinities, each one strictly bigger than the last. He called these infinite cardinal numbers, and he used the Hebrew letter aleph to name them. Aleph null, aleph naught. That's the cardinality of the natural numbers, the smallest infinity. The cardinality of the reals he called the cardinality of the continuum. And then he asked a question that would haunt mathematics for over a century. Is there an infinity between aleph null and the continuum? Is there a set bigger than the naturals, but smaller than the reals? He believed the answer was no, that the continuum was the very next infinity after the countable one. This belief became known as the continuum hypothesis, and Cantor spent years trying to prove it. He couldn't. It consumed him. He suffered severe bouts of depression, was hospitalized multiple times, and spent the last years of his life in a sanatorium in Halle, where he died in 1918. The tragedy of Cantor's later life is compounded by the opposition he faced. Leopold Kronecker, one of the most influential mathematicians in Berlin, was vehemently opposed to Cantor's work. Kronecker believed that mathematics should be grounded in finite constructions, that the natural numbers were the only truly real mathematical objects. He reportedly called Cantor a corrupter of youth and worked to block his publications and his career advancement. Cantor never got the prestigious professorship in Berlin that he deserved. He stayed at Halle his whole career, feeling isolated and underappreciated, even as younger mathematicians, Hilbert, Zermelo, others, recognized the profound importance of what he'd done. David Hilbert famously declared that no one shall expel us from the paradise that Cantor has created. But Cantor himself spent much of his life locked outside that paradise, battling both his own mental illness and the hostility of the mathematical establishment. As for the continuum hypothesis, the question of whether there's an infinity between the countable and the continuum, it turned out to have one of the strangest resolutions in the history of mathematics. In 1940, Kurt Gödel showed that the continuum hypothesis is consistent with the standard axioms of set theory. You can't disprove it. Then in 1963, Paul Cohen showed that it's also independent of those axioms. You can't prove it either. The continuum hypothesis is undecidable. It's neither true nor false within the framework that most mathematicians use. It's a question that the rules of the game simply don't answer. You can add it as an axiom or add its negation, and either way, you get a consistent system. Mathematics, at its foundations, has genuine gaps, places where the road simply forks, and you have to choose which way to go. That might sound unsettling, but there's something deeply honest about it. Mathematics isn't a finished building. It's a living structure, still under construction, and some of the most fundamental questions about its architecture remain open. Now, while Cantor was wrestling with infinities, his contemporary, Richard Dedekind's, was approaching the foundations from a different angle. Dedekind's contribution was quieter, but equally profound. Remember, the whole problem that had been simmering since the Pythagoreans was, what are irrational numbers really? Everyone used them. Everyone knew the square root of 2 existed as a length, but nobody had a rigorous definition of what an irrational number actually was as a number, not just a geometric magnitude. Dedekind's answer, published in 1872, was the Dedekind cut, and the idea is beautifully simple. Take all the rational numbers and divide them into 2 groups, a left set and a right set, such that every number in the left set is smaller than every number in the right set, and together they include every rational number. If the left set has a largest element, or the right set has a smallest element, then the cut corresponds to a rational number. But if the left set has no largest element and the right set has no smallest element, if there's a gap, then that gap is an irrational number. The cut itself is the number. You don't need to construct the irrational number from some other material. You define it as the partition, as the place where the rationals split apart. So the square root of 2 is the cut, where the left side contains all rationals whose square is less than 2, and the right side contains all rationals whose square is greater than 2. There's no rational number sitting at the boundary. The boundary itself, the cut, is the square root of 2. It's a way of conjuring irrational numbers into existence using nothing but rationals and the idea of division into 2 halves. And with this definition, you can prove all the properties you need. You can add cuts, multiply them, compare them, take limits, and the whole real number line emerges, complete and gapless, from the rationals alone. Between Dedekind's cuts and Cantor's set theory, the real numbers finally had a rigorous foundation. After 23 centuries of unease, stretching all the way back to that Pythagorean crisis, mathematicians could say precisely what the number line was and why it worked. The reals were complete. Every Cauchy sequence converged. Every bounded set had a least upper bound. Every gap was filled. And the filling, as Cantor showed, produced something uncountably infinite, something fundamentally larger than the rational numbers that generated it. But this triumph of rigor opened up new questions almost immediately, because once you have a precise definition of the real numbers, you can start asking what you can compute with them. And that question, what is computable, would lead, in the 20th century, to an entirely new kind of number and an entirely new way of thinking about mathematics itself. Because here's the thing. When we talk about numbers, we tend to imagine them all sitting there on the number line, equally real, equally accessible. But are they? Can you actually write down a procedure, a set of instructions, that produces any real number you want? And the answer, it turns out, is no. Most real numbers are, in a very precise sense, unreachable. You can't compute them. You can't describe them. You can't even name them. They exist. Cantor proved they exist. But they hide in the continuum like dark matter, making up almost all of it while remaining forever beyond your grasp. The person who made this idea precise was Alan Turing, and the year was 1936. Now, Turing is famous for a lot of things: for breaking the Enigma code during World War II, for laying the foundations of computer science, for his tragic persecution by the British government. But before all of that, When he was just 23 years old and a student at King's College, Cambridge, he wrote a paper that changed everything. Its title was dry and technical, on computable numbers with an application to the Entscheidungsproblem. But what it contained was revolutionary. And the funny thing is, the paper wasn't really about computers. It was about numbers. Specifically, it was about which real numbers you can actually calculate. Here's how Turing set it up. Imagine you want to compute a real number, say, pi. You need some kind of procedure, some mechanical process that spits out the digits one at a time. For pi, we have such procedures. There are formulas, algorithms, series expansions that let you compute the first digit, then the second, then the third, and keep going forever. You'll never finish, because pi has infinitely many digits, but at any point you can tell me what the next digit is. That's what it means for a number to be computable. There exists a finite set of instructions, what Turing called a machine, that, given enough time, will produce any digit you ask for. Now, Turing didn't have actual electronic computers to work with in 1936. They didn't exist yet. So he invented an imaginary one. The Turing machine, as it came to be called, is beautifully simple. Picture an infinitely long strip of tape divided into squares, each square holding a symbol, say a 0 or a 1 or a blank. There's a little read-write head that sits over one square at a time, and it follows a table of rules. Each rule says, if you're in this state and you see this symbol, then write that symbol, move one square left or right, and switch to a new state. That's it. That's the whole machine. A tape, a head, and a finite list of rules. And here's what's remarkable. This absurdly simple device can compute anything that any computer can compute. Your laptop, your phone, the most powerful supercomputer on Earth. They can all be simulated by a Turing machine. They might be faster, sure, but they can't compute anything that a Turing machine can't, given enough time and tape. This is the Church-Turing thesis, and while it's technically unprovable, it's a claim about the nature of computation itself. Nobody has ever found a convincing counterexample. Every reasonable definition of mechanical computation that anyone has ever proposed turns out to be equivalent to Turing's little tape machine. So a computable number is simply a real number, whose decimal expansion, or binary expansion, it doesn't matter, can be generated by some Turing machine. Pi is computable. The square root of 2 is computable. Euler's number E is computable. Every number you've ever encountered in a math class, every number you've ever used in engineering or physics, is computable. Even numbers that are irrational, even numbers that are transcendental, as long as there's an algorithm that can crank out their digits, they're computable. But here's where Cantor's ghost walks back into the room. How many Turing machines are there? Well, each Turing machine is defined by a finite table of rules. You can write those rules down as a finite string of symbols, and finite strings of symbols drawn from a finite alphabet. You can list them. You can enumerate them. 1, 2, 3, 4. There are countably many finite strings, which means there are countably many Turing machines, which means there are only countably many computable numbers, aleph null of them, the same infinity as the counting numbers. But the real numbers are uncountable. Cantor proved that. So the computable numbers, all the numbers we can ever actually specify, calculate, define, name, form a vanishingly tiny subset of the reals. Almost every real number, in the most rigorous sense of almost every, is uncomputable. If you could somehow throw a dart at the number line and hit a point with perfect precision, the probability of hitting a computable number would be 0. Not small. 0. The number line is almost entirely made up of numbers that no algorithm, no computer, no mind can ever produce. Think about what that means for a second. We built this beautiful, complete, gapless number line. Dedekind filled every hole. Cantor showed it was uncountably infinite. And now Turing is telling us that almost none of it is accessible to us. It's like discovering that the universe is mostly dark energy and dark matter. And the stuff you can actually see and touch is a tiny fraction of what's out there. The computable numbers are the visible matter of mathematics. Everything else is shadow. Now, Turing didn't introduce computable numbers just for the fun of it. He had a specific target: the Entscheidungsproblem. The decision problem had been posed by David Hilbert in 1928. Hilbert, who was probably the most influential mathematician of the early 20th century, wanted to know whether there existed a general algorithm that could determine the truth or falsity of any mathematical statement. Feed it a proposition, and it tells you, true or false, a universal truth machine. Hilbert believed the answer was yes. He was an optimist about the power of formal systems. His famous declaration, "Wir müssen wissen, wir werden wissen," we must know, we shall know, captured his faith that mathematics had no permanently unsolvable problems. But Turing showed the answer was no, and he did it through numbers. He proved that there exist well-defined mathematical questions that no Turing machine can answer. The most famous is the halting problem. Given a description of a Turing machine and an input, will the machine eventually stop, or will it run forever? Turing proved, using a diagonal argument reminiscent of Cantor's, that no algorithm can solve this problem in general. Some questions are undecidable, not just hard, not just beyond our current abilities, fundamentally, permanently, provably beyond the reach of any mechanical computation. And this connected to something that had already shaken the foundations of mathematics a few years earlier. In 1931, Kurt Gödel, a quiet, almost painfully shy logician from Brno, in what was then Czechoslovakia, published his incompleteness theorems. Gödel showed that in any consistent formal system, powerful enough to express basic arithmetic, there exist true statements that cannot be proved within the system. Mathematics, in other words, contains truths that are beyond proof. Not because we haven't been clever enough to find the proofs, but because the proofs don't exist within the system. The system is incomplete, and if you try to patch it by adding new axioms, new unprovable truths appear. It's incompleteness all the way up. Gödel's proof was itself a masterpiece of using numbers in an unexpected way. He assigned a unique number to every symbol, every formula, every proof in the formal system, a technique now called Gödel numbering. He turned statements about mathematics into statements about numbers, and then showed that the system could talk about itself, could construct a sentence that essentially said, "This statement has no proof in this system." If the system is consistent, that statement must be true but unprovable. It's a mathematical version of the liar's paradox, except it actually works rigorously without contradiction. So between Gödel and Turing, the 1930s delivered a 1-2 punch to Hilbert's program. Mathematics was incomplete, computation had limits, and numbers, the very things that had seemed so solid, so dependable, so fully understood after Dedekind and Cantor, turned out to harbor deep mysteries about what can be known and what can be calculated. But here's the thing. these weren't just abstract philosophical results. Turing's work led directly, within a decade, to actual physical computers. The theoretical machine he'd invented as a thought experiment became, during and after World War II, a blueprint for real machines. The Colossus at Bletchley Park, the ENIAC in Philadelphia, the Manchester Baby in 1948, which Turing himself worked on. The abstract question, what can be computed, gave birth to the most transformative technology of the 20th century. Numbers, once scratched into clay tablets by Sumerian scribes, were now flowing through vacuum tubes and transistors at thousands of operations per second. And as computers grew more powerful, they opened up entirely new territories in the landscape of numbers. Things that would have been inconceivable to calculate by hand became routine. You could compute millions of digits of pi. You could search for enormous prime numbers, the great Internet Mersenne. Prime Search, running on thousands of volunteers' computers, has found primes with tens of millions of digits. You could explore the Mandelbrot set, that infinitely intricate fractal shape that lives in the complex number plane, the same plane where Bombelli's imaginary numbers finally found a geometric home centuries earlier. And this brings us to something that might seem like a detour, but really isn't: the way numbers live inside computers. Because when you store a number in a computer, you're not storing it the way a mathematician thinks about it. You're storing an approximation, a finite string of ones and zeros, typically 32 or 64 bits long, representing the number in what's called floating point format. And floating point arithmetic has its own peculiarities, its own failure modes, its own surprising little gotchas. Take something as simple as adding 1/10 to itself 10 times. You'd think you'd get one, right? But in many programming languages, if you actually do that calculation, you get something like 0.99999999998, or 1.000000002, not exactly 1, and 0002, not exactly 1. And the reason is beautiful in a frustrating kind of way. It's because 1/10, which is such a clean, tidy number in base 10, turns out to be a repeating fraction in base 2. Just like 1/3 is 0.333 repeating forever in decimal, 1/10 is 0.00011000110011 repeating forever in binary. And since a computer only has 64 bits to work with, it has to round. It chops off that infinite repeating tail, and what's left is not quite 1/10. It's incredibly close, but not exact. And when you add up those tiny errors, they accumulate. Now, most of the time this doesn't matter. For everyday calculations, adding up your grocery bill, rendering a video game, running a spreadsheet, floating point arithmetic is more than accurate enough. But there are situations where those tiny rounding errors can cascade into genuine disasters. And this is where the story gets sobering. On February 25, 1991, during the Gulf War, a Patriot missile battery in Dhahran, Saudi Arabia, failed to intercept an incoming Iraqi Scud missile. The Scud hit an American barracks and killed 28 soldiers. The investigation afterward revealed that the cause was a floating point rounding error in the Patriot's tracking software. The system used a 24-bit fixed-point register to store time, measured in tenths of a second. But 1/10, as we just talked about, can't be represented exactly in binary. The error was tiny, about 0.00000095 seconds per tenth of a second, almost nothing. But the system had been running continuously for about 100 hours, and over that time, the error accumulated to about 0.34 seconds. Doesn't sound like much, but a Scud missile travels at roughly 1,700 meters per second. In a third of a second, it covers over half a kilometer. The tracking system was looking for the missile in completely the wrong part of the sky. It never found it. 28 people died because of the difference between 1/10 and its closest binary approximation, multiplied by time. That's a story worth sitting with for a moment. Not because it's dramatic, though it is, but because of what it reveals about the nature of numbers inside machines. Computers don't work with the real number line. They work with a finite subset of rational numbers, a grid of representable values, spaced unevenly across the number line, clustered more densely near zero, and spreading further apart as numbers get larger. Between any two floating point numbers, there are infinitely many real numbers that simply cannot be represented. The computer rounds to the nearest one it can express and moves on. And usually that's fine. But sometimes it isn't. The Ariane 5 rocket explosion in 1996 is another famous case. The European Space Agency's brand new rocket, carrying 4 expensive scientific satellites, veered off course and self-destructed just 37 seconds after launch. The cause? A piece of software tried to convert a 64-bit floating point number representing the rocket's horizontal velocity into a 16-bit signed integer. The number was too large to fit. The conversion overflowed. The guidance system received garbage data. The rocket thought it needed to make a massive course correction. It turned so sharply that aerodynamic forces tore it apart, and the self-destruct system triggered. $500 million gone in half a minute because of a number that was too big for its container. These stories connect to something deep about our entire journey through the history of numbers. From the very beginning, from those first tally marks scratched into bone 30,000 years ago, numbers have always been representations, abstractions. A tally mark isn't the thing it counts. It's a symbol that stands for a quantity. A Babylonian cuneiform wedge isn't the number 60. It's a mark in clay that means 60 within a system of agreed-upon conventions. And every number system humanity has ever devised has had limitations. The Babylonians had no zero and struggled with ambiguity. The Romans had a system that made arithmetic nearly impossible. The Egyptians could handle fractions, but only unit fractions, which made some calculations absurdly complicated. Every representation is a trade-off. Every system captures some aspect of numerical reality and misses others. Floating point arithmetic is just the latest chapter in that story. It's an incredibly clever system. It can represent numbers as tiny as 10 to the negative 308 and as large as 10 to the positive 308, all within 64 bits. That's a staggering range. But it achieves that range by sacrificing precision, especially at the extremes, and the gaps between representable numbers aren't uniform. Near zero, the representable numbers are packed incredibly close together. Out near 10 to the 300th power, the gap between adjacent representable numbers is larger than most numbers you'd ever encounter in everyday life. The system is, in a sense, a map of the number line. And like all maps, it distorts reality in order to be useful. Here's what's really interesting, though. Despite all these limitations, despite the rounding errors and the overflow bugs and the fundamental impossibility of representing most real numbers exactly, computers have become our most powerful tools for exploring the number landscape. Think about what they've enabled. The search for prime numbers has been transformed. As of the early 2020s, the largest known prime number has over 41 million digits. You couldn't write it down by hand in a lifetime. It exists only as a pattern of bits in computer memory, verified by algorithms that themselves rely on deep number theory. the very theory that Fermat and Euler and Gauss developed centuries ago, now running on silicon. Or think about pi. When Archimedes calculated pi, he used a 96-sided polygon and got it to about 3 decimal places. By the 15th century, the Persian mathematician Jamshid al-Kashi had pushed it to 16 decimal places using similar geometric methods, which was the world record for over a century. In 1949, ENIAC, one of the first electronic computers, calculated pi to over 2,000 decimal places in 70 hours. By 2024, pi has been computed to over 100 trillion digits. 100 trillion. And here's the strange thing. We don't need those digits for anything practical. Even NASA, for its most precise orbital calculations, uses only about 15 decimal places of pi. With just 40 digits of pi, you could calculate the circumference of the observable universe to an accuracy smaller than a hydrogen atom. So why compute trillions of digits? Partly to test computers and algorithms, partly because the digits of pi are a kind of mathematical wilderness. People study their statistical properties, looking for patterns, testing whether pi is what's called a normal number, meaning every possible sequence of digits appears with equal frequency. So far, pi looks normal, but nobody has been able to prove it. It's one of those questions that's easy to state and incredibly hard to resolve. And that connects back to something Cantor showed us, and Turing after him. The number line is overwhelmingly populated by numbers we can't compute, can't name, can't even specify. The computable numbers, every number any algorithm could ever produce, digit by digit given enough time, are countable. They form a set the same size as the natural numbers, but the real numbers are uncountable. So almost every real number, in a very precise mathematical sense, is forever beyond the reach of any computation. They exist. They have definite positions on the number line, but no finite procedure can ever produce their digits. They are, in a sense, the dark matter of mathematics. They make up almost everything, but we can never directly observe them. And yet, here's what I find quietly astonishing about all of this. Despite those limitations, despite Gödel telling us that any sufficiently powerful mathematical system contains truths it cannot prove, despite Turing telling us that most numbers can never be computed, despite Cantor showing us that infinity comes in sizes we can barely comprehend, despite all of that, numbers work. They work extraordinarily well. The mathematics of numbers, developed over thousands of years by countless human minds, allows us to build bridges that don't fall down, to send spacecraft to the outer planets with trajectories calculated years in advance, to encode and transmit information across the globe in milliseconds, to model the behavior of atoms and galaxies and everything in between. The number system we use today, the Hindu-Arabic numerals, the decimal point, the real number line, complex numbers, all of it, is one of humanity's greatest collective achievements. And it was built slowly, piece by piece, by people who were often just trying to solve a practical problem. How many sheep do I have? How do I divide this grain fairly? How tall is this pyramid? How do I solve this equation that seems impossible? Think about the arc of it. A bone with notches carved by someone on the shores of a prehistoric lake, keeping track of something we'll never know. Sumerian accountants pressing tokens into clay envelopes to record transactions. Babylonian scribes discovering that the same mathematical relationships appear in the movements of planets. Indian mathematicians recognizing that nothing, the absence of quantity, deserves its own symbol, and that this symbol changes everything. Al-Khwarizmi writing a book that would give us the word algorithm. Fibonacci carrying those ideas across the Mediterranean. Cardano and Bombelli wrestling with numbers that seemed impossible, but turned out to be essential. Cantor, alone and ridiculed, proving that infinity is not one thing but an endless tower of ever larger infinities. Turing, a young man in Cambridge, imagining a machine that doesn't exist in order to answer a question about what can be known. Every one of those people was working with numbers, the same numbers, the ones that started as scratches on bone and became the language of science, engineering, commerce, and computation, the ones you use every day without thinking about it. When you check the time, when you glance at a price tag, when your phone calculates a route or streams a song. Numbers are so woven into the fabric of modern life that they're invisible, like the air. But they have this extraordinary history, this deep, winding human story behind them. And maybe that's the most comforting thought to drift off with, that something as simple as counting, 1, 2, 3, connects you to the earliest humans who ever looked at the world and tried to make sense of it. That the number line stretching out in both directions, through the integers and the fractions and the irrationals and the transcendentals and the imaginaries, is a landscape that humanity has been exploring for tens of thousands of years and still hasn't fully mapped. That there are questions about numbers, simple, clear, statable questions that remain unanswered and may remain unanswered forever. And that's not a failure. That's the nature of the thing. Numbers are infinite, and we are finite. And the conversation between those two facts is the story of mathematics itself. So let that settle over you. The long, slow story of numbers, from tally marks to Turing machines, from clay tablets to floating point arithmetic, from the first shepherd counting a flock to the latest computation of pi's trillionth digit. It's all one story, one continuous thread of human curiosity, stretching back to the beginning and forward into whatever comes next. And you're part of it. Every time you count, every time you measure, every time you notice a pattern or wonder about a number, you're continuing that ancient conversation. The oldest conversation there is, really. The one between a human mind and the quiet, patient, endlessly surprising world of numbers. Let it carry you gently now, into sleep, into rest, into whatever dreams might come. The numbers will still be there in the morning. They always are.